Welcome to another exciting tutorial. In this video, we are diving deep into Spring Data JPA, one of the most powerful tools for working with relational database in Spring Boot. Throughout this tutorial, you will learn how to work with entities, create and use repositories, define repository methods, and even write custom queries. By the end of this video, you will have solid understanding of how to handle relationships like one-to-one, one-to-many, and many-to-many. We will explore concepts like cascading, custom queries, and bi-directional relationships, all essential for building real-world applications. Whether you are just getting started with Spring Data JPA or looking to strengthen your skills, this tutorial has you covered. Make sure to stick around because I will also share tips and techniques that you can apply immediately to your projects. And if you are ready to level up, there are advanced topics waiting for you in upcoming videos. So don't miss out. Alright, let's get started and unlock the full potential of Spring Data JPA. Before we start, there are a few prerequisites. You should have a good understanding of Java and Spring Boot. You should also know how to write SQL queries. So, who is this course for? If you are beginner or intermediate Spring Boot developer, this course is for you. Let me explain what we are going to do. Check this year diagram. This is our employee table. We will create an entity for this employee table. This employee has a few columns like ID, first name, last name, email, hire date, and salary. The email must be unique. Each employee has an address. There is a one-to-one relationship between employee and address. One employee can have only one address, and each address belongs to one employee. This is a bi-directional relationship. Next, each employee can be assigned multiple tasks. This creates a one-to-many relationships between employee and task. This relationship is also bi-directional, meaning multiple tasks can be assigned to one employee, which means many to one from task side. Finally, let's talk about the project. There is a many-to-many relationship between project and employee. One project can be assigned to multiple employees and one employee can have multiple projects. That's what we are going to build in this tutorial. Let's dive in and start building. For creating a new Spring Boot project, I'm going to use my favorite online tool, Spring Initializer. You can access it at start.spring.io. For this project, I am using Maven as the build tool and Java as the programming language. For the Spring Boot, always try to use the latest Spring Boot version. At the time of this recording, the version is 3.4.1. Let's start by filling in the project metadata. First field is group. Let's change it, my domain name. Then update the artifact name. For the packaging type, I will use jar. For the Java version, my installed Java version is 21. Now let's add dependencies. Click the Add Dependencies button or use shortcut Ctrl+B on Windows or Command+B on Mac. This opens a modal window where you can find many available dependencies for Spring Boot, like Spring Web for building web applications, GraphQL, TimeLeaf, and more. You can check it by yourself and include what you need. Since I already know the dependencies I need, I can include it easily by searching. Here, I will write the dependency name here in the search box. First, I will add Spring Web. Next, I will search for and add Spring Data JPA. Finally, I will add the PostgreSQL database driver as I will be using PostgreSQL for this project. After selecting these dependencies, click the Generate button to download the project. Once the project is generated and downloaded, import it into your favorite IDE. Here, I have imported the project into my IDE. I'm using IntelliJ IDE I Ultimate version. It is paid. IntelliJ also provides free community edition. You can also use that. But in that case, you will miss some of the cool features that IntelliJ IDE I Ultimate version provide. You can also use Spring Toolsuite, Eclipse, or any IDE you are comfortable with. Now, let's explore the project structure. The first file is pom.xml, which contains metadata defined in Spring Initializer. It includes the Java version and the list of dependencies like Spring Web, Spring Data JPA, and the PostgreSQL driver. Next, we have the src folder, which contains the main and test subfolders. Inside the main, there are Java and resources subdirectories. The Java directory holds the root package, where all Java code will go. Currently, here we have Spring Data JPA Java class. This contains main method. The resources directory contains important files like application.properties, where we will define configurations such as the database URL, username, and password. It also includes directories for template and static. This template subdirectory holds all the HTML, and assets like images, CSS, and JavaScript goes to the static directory. Now let's run the project. We can start the project by clicking this play icon beside the main method. Click the run icon to start the project. Our application failed to start. Let's check the console. What happened? It is failed to configure data source. URL attribute is not specified. What does it mean? Why the error is happening? Let's open pom.xml file. Here, we have included this Spring Data JPA dependency for our project. This requires you to configure the database to start the application. As we have included it but have not configured the database yet, so our application failed to start. For the time being, let's remove the dependency temporarily, commenting it out. Now we need to reload the project. To reload the dependency, there are a couple of options. We can click on this refresh icon to reload, or click on this Maven icon on the right sidebar and click on this refresh icon. Alternatively, you can right click Maven and reload the project. After reloading the project dependencies, the application should start successfully. Let's start the project. You can start the project by clicking this play icon beside the main method or by clicking this play icon on the top. This time, the project started successfully. The project is started on port 8080. Now, if we try to access this, we'll get a white label error because we have not defined any endpoint for handling the URLs. Let me show you what I mean. Let's try to access it in the browser. Our project is running at localhost and port is 8080. Here, we are getting this white label error. The status code is 404. That means the URL we are searching for is not available. Let's fix this. In our root package, creating a new Java class. Name home controller. And annotate it with REST controller. Add a get mapping for the root URL. Public method, it returns string, name home. This method returns a simple hello world message. Restart the project. Refresh the browser. You should now see hello world displayed. Next, we'll configure the database. First, I need to create a PostgreSQL database. I have already installed the database server on my local machine. To access it, I can use either a command line tool or a GUI interface like pgadmin. IntelliJ IDE Ultimate includes a built-in database tool, which I will use here. However, you can use any database client or command line tool you are comfortable with. Click on the database icon in the sidebar, click the plus icon, select data source and search for PostgreSQL. Let's keep the default setting for now. Provide our database username. In my case, it is Postgres. Enter your database password. Since the database is running on the default port, that is 5432, there's no need to change the port. Test the connection to ensure it works. If the connection is successful, click OK. Now you will see the database listed in the database tool. Let's create a new database. Right click on the database section, select new database, give the database a name. Let's call it employee_management. Click OK. Here, our new database is not showing up. Click on this icon, this text on one of two. In this drop down, click refresh. Select employee management. Then click OK. Now refresh and you will see the new database. At this point, there are no tables in the database. Let's check the public schema. There are no tables yet. We'll create those shortly. Next, let's configure the application to connect to this database. Open the application.properties file. I actually don't need this line. Let's remove it. For database configuration, we'll need to provide the database URL, spring.datasource.url. The URL is JDBC PostgreSQL localhost then the port 5432/employee_management. Here I have made a mistake. Let's correct it. PostgreSQL port is 5432. Then the database username spring.datasource.username. My username is Postgres and database password. Providing my database password. As I am using PostgreSQL, I need to provide a driver class name for the PostgreSQL. That is org.postgresql.driver. Also, let's exclusively tell which database we are going to use. This is PostgreSQL. And finally, we need to tell the Spring about our database platform. This is org, Hibernate, dialect, Postgres dialect. That's all the information we need in our application.properties file to connect with the database. Beside these basic configurations of the database in the application, I want to specify some additional configurations. I want to view the executed SQL query in my console. By default, it is not enabled. We need to enable it. We can do this using the configuration spring.jpa.showSQL. Set it to true. To view the query formatted, spring.jpa.properties Hibernate format SQL, set it to true. Now we will be able to view the executed query in the console. The final configuration we need is Spring JPA Hibernate DDL Auto. This DDL Auto controls how Hibernate will handle our database schema. Here we can choose one of these 5 available options: create, create drop, none, update, and validate. Now let me explain those options provided by DDL Auto. Create, if we choose this option, it will drop and recreate the database schema every time the application starts, which can be useful for testing, but it also means any data will be lost on restart. Then we have create drop. This one is similar to create, but it also drops the schema when the application stops, ensuring a clean database every time. None, this simply disables the DDL operation. Next we have the update. This is what we are going to use in this tutorial. Setting DDL Auto to update means that Hibernate will automatically create any new tables or columns in the database based on our entity classes, but won't delete or modify any existing data. This is super convenient for development, where we often make changes to our entities and want those changes to reflect in the database without manually updating the schema. Then we have validate. This only checks the schema matches our entities. If it does not, the application won't start. Here I am choosing the update. So by using update, we are telling Hibernate to take care of the schema updates without touching my existing data. It's a good balance for development, but not something we would use in production. Now let's bring back our Spring Data JPA dependency. Opening pom.xml. Here is the dependency declaration we have commented out. Uncomment it and reload the Maven dependency. Now start the project. Here again there is some problem. Driver claims do not accept JDBC URL. Maybe I have provided the wrong URL. Let's fix it. Opening application.properties. Here is the URL. Let's remove it. Provide it again. JDBC PostgreSQL // localhost then the port 5432 / and database name employee_management. Start it again. This time started successfully and it has successfully connected with database. Now let's create our entity. The first entity I am going to create for employee. Entity is simple plain Java class with special annotation. In our root package, creating a new Java class. Name it employee. Our employee will have couple of properties. Every employee will have ID. Private, it will be long, name it ID. Then our employee will have first name, private, string, first name. Then last name. Our each employee will have email address. Private, string, email. Next, we will store when the employee have joined in the company. It will be private, then local date, and it is our hire date. And finally, we will store the employee salary. Private, double, salary. Now, creating the constructor. Right click inside the class, generate constructor. Select all the fields. Actually, we do not need to select the ID. It will be auto-generated. Select other properties and click OK. We also need another constructor without arguments. Right click, generate constructor. Select none. Our constructor is generated. Now we need to generate the getter and setter of the fields. Right click, generate getter and setter. Select all, click OK. This is our Java class. There's nothing special about it. The employee class will represent the employee table in the database. So we need to map it to the database. Java Persistence API provides a way to do this easily. For that, we need to make it an entity by using entity annotation. Make sure you import this from Jakarta persistence entity. Here it is showing an error. Let's check what is the problem. The error says the persistent entity employee should have a primary key. Every database table must have a primary key. Since this employee class will map to an employee table in the database, we need to specify which property of this class will act as the primary key. We have already defined the properties of the employee class, but we have not designated any of them as a primary key yet. I will make the ID property the primary key of the employee class. To do this, we need to annotate the ID property with the ID annotation. This tells JPA that this property will act as primary key. Once we add the annotation, the error is resolved. Now let's stop the project and rerun it. In the console, you will notice a query indicating that a table has been created in the database. Let's check the database to confirm. Refresh the database and here it is. The employee table has been created successfully. You can also see the columns of the table. Next, let's play around with this entity. By default, the class name is used as the entity name in the database. However, it's considered a good practice to explicitly provide an entity name. I'm going to set the entity name explicitly. Let's name it the same as the class name, employee. We can also specify the name of the table that we want the employee class to map to by using the table annotation. If you don't provide any table annotations in a JPA entity class, JPA will by default attempt to map the entity to a table with the same name as the entity class. Here, we will explicitly provide the table name as employee. Now, let's move on to the fields of the employee class. The first field is our ID. The value of the ID can be either be set manually or generated automatically. In this case, I want it to be generated automatically. If you are familiar with MySQL, you might know about its auto-increment feature for automatically generating values for the ID field. However, since we are using PostgreSQL, we will use a sequence to auto-generate the ID value. We need to specify how we want this ID to be auto-generated. For this, we use the generated value annotation. Here, we define the generation strategy. There are few options for generation strategies. First one is auto. This is the default strategy. It allows the persistence provider like Hibernate to choose the most suitable generation strategy based on the database and its capabilities. It adapts to various database environments, making it a convenient choice. Then we have identity. This strategy relies on the database's auto-increment feature to generate primary key values. It is suitable for databases like MySQL, PostgreSQL, and SQL Server, which support auto-incrementing columns. Sequence. This is the strategy we are going to use. It employs a dedicated database sequence to generate primary key values. It's a common choice for PostgreSQL and provide control over key generation. Then we have table. This strategy maintains a separate database table to manage primary key values. It is less frequently used compared to other strategies, but can be helpful in specific scenarios where fine-grained control over key generation is required. Finally, we have UUID. That means Universal Unique Identifier. This strategy generates a universally unique identifier using the UUID algorithm. It is particularly useful in distributed systems where globally unique IDs are necessary. In this project, we will use the sequence strategy as it aligns with the PostgreSQL's feature. Let's run the project and check the console. Here, you can see a database query is printed. A new sequence has been created. It starts from 1 and increments by 50. This means the ID of the first entry will be 1 and the ID of the second entry will be 51, incrementing by 50. However, I want the ID to increment by 1 instead. This means the ID of the first entry should be 1, the second entry 2, and so on. Additionally, I don't want to use the generated name for the sequence. I would like to provide my own sequence name. To achieve this, we need to use another annotation, SequenceGenerator. The SequenceGenerator annotation accepts several properties. First one is name. It is required. A unique name for the SequenceGenerator. This name is used to link the generator to the entities that use it. Here, I will name it employee_sequence. Then, the second parameter is sequence name, the name of the database sequence object from which to obtain primary key values. If not specified, the persistence provider will choose a default. I will name it employee_sequence. Then we have allocation size. the number of values to allocate in memory for each strip to the database. Setting this to 1, we instruct JPA to increment the ID by 1. Now, let's update the generated value annotation to link it with our custom sequence generator. Move it to the next line and define the name of the sequence generator. I will use employee sequence. Let's restart the project and check the console again. Now, a new sequence is created with the name employee_sequence as we defined, and it increments by 1. We can also define the name of the column that this field will map to using the column annotation. Here, we can specify the column name. I will use the same name as the field, ID. Additionally, since the ID field is auto-generated and should not be updated after it is generated, we can enforce this by setting the updatable property to false in the column annotation. Now, let's work on the first name field. This field should not be null and the maximum length will be 100 characters. To enforce these constraints, we will use the column annotation. Set name to first_name. Make it nullable to false and set the length to 100. For the last name field, the requirements are similar. To save time, copy the column annotation from first name and paste it above the last name field. Then change the column name to last name. For the email field, again paste the copied column annotation, change the column name to email and set nullable to false. Since the email address don't have strict length requirements, we can remove the length property for this field. For the hire date field, we'll use the column annotation, set the column name to hire_date and make it nullable to false. For the salary field, also use the column annotation, set the column name to salary and make it nullable equals false. Now, the email of each employee must be unique. To define this, we need to add a unique constraint. At the top of the class, in the table annotation, add the unit constraint property. Use curly braces to specify the constraint. Inside the braces, add the unique constraint annotation. Give the unique constraint a name, such as employee_email_unique. And specify name of the column that should be unique, in this case, email. Now, let's start the project and check the console. In the console, you can see that the table has been altered. The first name column now has maximum length of 100 characters. The same applies to the last name. A new unique constraint, employee email unique, has been added for the email column. With these changes, we have successfully created the employee entity. Next, we will focus on the repository. Let's talk about a repository pattern. It's a design pattern that connects the data access and business logic in our application. By using this pattern, we can abstract a data layer, providing more object-oriented way to access data. In Spring, we use repository interface to interact with the database, leveraging the powerful feature of Spring Data JPA. At its core, the repository pattern acts as a bridge between your application's business logic and data storage. It encapsulates data access logic within repositories which are responsible for querying and manipulating data from the underlying data source, like database or web service. By doing this, it shields our application from the complexities of data storage. This makes it easier to switch between data access to make changes to the database schema without affecting our application's code. The repository interacts with data mappers and query objects to perform operations like retrieving and saving data. Even though this might seem like overkill for our simple app, using the repository pattern provides a protective layer that ensures our application can scale effectively and handle more complex scenarios in the future. The repository pattern allows our business logic to query and persist data without needing to know the details of the underlying database operations. It promotes cleaner and more manageable code. In the past, creating a data access layer for an application was difficult because it requires writing a lot of repetitive code. Domain classes were often simple and not designed to fully object-oriented or domain-driven principles. The goal of Spring Data's repository system is to make it much easier to create the data access layer for different types of database. In this section, we learn the main ideas and interfaces of Spring Data repositories. Let's start by creating a repository interface. Open the sidebar and go to src, main, Java. In our root package, create a new Java class, but make sure to select interface instead of class. I will name this interface employee repository. This interface will extend JPA repository. Make sure to import it from org.springframework.data JPA repository. The JPA repository is a core interface that provides built-in methods to work with JPA entities. It makes it easy to perform database operations using JPA. It's a generic interface, so we need to specify two things. The entity class we want to manage, in this case, employee. The data type of the entity is primary key. For employee, the primary key is ID, which is type of long. Now, our employee repository is ready. Let's look deeper into what JPA repository does. If we Command+click on Mac or Ctrl+click on Windows on JPA repository, it will open the source code for the interface. You can see that JPA repository extends three other interfaces: list CRUD repository, list paging and sorting repository, and query by example executor. For now, let's focus on list CRUD repository and list paging and sorting repository. Click on list CRUD repository to see its source code. List CRUD repository extends CRUD repository. If we check the CRUD repository source code, you will see that it extends another interface called repository. The repository interface does not define any methods. It acts as marker interface and helps Spring Data discover and manage your repositories. When Spring scans your application, it looks for interfaces that extend repository. Then, based on your method names and parameters, Spring automatically creates the implementation for these repositories. Now, let's look at CRUD repository. The CRUD repository interface provides methods for basic create, read, update, and delete operations. It saves time by letting you interact with the database without writing a lot of code. Some important method provided by CRUD repository includes save. This saves an entity to the database. If it already exists, it updates the entity. Then we have save all, save a collection of entities. Find by ID retrieves an entity by its ID. Find all retrieves all entity. Delete by ID deletes an entity by its ID. And delete deletes the given entity. There are more methods available. Feel free to explore them. Now let's talk about list CRUD repository. This interface extends CRUD repository but has one key difference. Instead of returning iterable for methods that retrieves the multiple entities, it returns a list. For example, the findAll method in CRUD repository returns an iterable, but this list CRUD repository, it returns a list. Using a list is more convenient because you can directly access elements by index and use methods like get, indexOf, or sublist without converting the result. Finally, let's go back to JPA repository. The JPA repository also extends list paging and sorting repository, which in turn extends paging and sorting repository. This paging and sorting repository also extends the repository interface. The paging and sorting repository provides method to work with the paginated and sorted data. This is useful when dealing with large dataset. That's it for now. With this, we have explored the basics of JPA repository and its related interface. Next, we'll focus on using repositories in our project. At this point, we have set up our employee entity, created a database table with all the necessary columns, and defined a repository for employee. Now, let's perform some database operations. In real-world application, we typically have controllers and service layers. The controller handles HTTP request and calls the service layer to process the request. The service layer then performs any necessary calculations and interacts with the repository to handle database operations. For example, if we wanted to handle CRUD operations, we would define endpoint in the controller for creating, reading, updating, and deleting data. The controller would call the relevant service method and the service would use the repository to work with the database. But since this tutorial focuses on Spring Data JPA, we will skip this part. Instead, we will use command line runner to perform database operations. Now, what is a command line runner? It's a special tool provided by Spring Boot that allows us to run code immediately after application starts. This makes it useful for quickly testing and developing code. Let's open Spring Data JPA application class. We need to create a bean. Let's create a command line runner. We will define it as public method because all Spring Bean must be public. The method will return a command line runner. The method also requires a parameter. We need to pass the employee repository as a dependency, which allows us to interact with the database. Inside the method, return an arrow function, args, arrow, then curly braces. Inside these curly braces, we will write the code for our database operations. This code will execute automatically when the application starts successfully. To begin, let's save an employee to the database. We will create a new instance of the employee class and set the necessary properties. First name is John, last name Doe, email john@learnwithiftekhar.com. We will also set the hire date using the local date class. It requires three parameters: the year, the month, and the day of the month. Let's set the hire date to January 1, 2022. The year is 2022. January is the first month of the year and the date is 1. Finally, we will set the salary. Let's assume John's salary is $2,000. Our employee object is ready. We will save it to the database using save method from the employee repository. Now, let's start the project. In the console, you will see the SQL queries printed. This includes an insert statement for the employee table and a query to fetch the next sequence number for generating the ID. Let's verify this in the database. Open our database tool and refresh the employee table. Check the data and you will see the new entry. The ID is automatically generated using the sequence. The email, first name, last name, salary and hire date match exactly what we provided. And that's it. We have successfully saved an employee to the database. Now, let me show you something interesting. Stop the application and start it again. Take a look at the console. There is an exception. Let's check what happened. The error message says, duplicate key value violates unique constraint. Employee email unique. What does that mean? Every time we start the application, the command line runner gets executed. This runner is trying to save the same employee to the database. But since we have already saved this employee before and the email field is declared as unique, the database is showing an exception. Let me show you where this is defined. In the employee entity, here is the email field and it's marked as unique through a unique constraint at the top in this table annotation. Because of this, when the application tries to save an employee with the same email address again, the database prevents it and throws an error. As a result, the entry cannot be saved. Now, let's comment out the previous code that was causing the duplicate key exception. Next, we will add a couple of new employees. To do this, we will copy the existing code block and make some changes. First, let's create an employee named Jane. Her first name is Jane. Her last name is Doe. Her email address is jane@learnwithiftekhar.com. Let's assume we hired her in 2023 and her salary is $2,200. Now let's add another employee named Anna. Her first name is Anna. Her last name is Doe. Her email address is anna@learnwithiftekhar.com. We hired her in 2024 and her salary is $1,900. To save those two employees, we will use a handy method provided by Spring Data JPA that allows saving multiple records at once. Let me explain how it works. If we look at the employee repository, it extends from JPA repository. JPA repository extends from list CRUD repository, which further extends from CRUD repository. In the CRUD repository, there's a method called save all. This method allows us to save multiple entities in a single call by passing a list of entities. Now back to the code. We'll use the save all method from employee repository and pass the two new employees as a list. Let's start the project. In the console, you can see two insert statements, one for each employee. Finally, let's check the database. Open the employee table. Here you can see the entries for both Jane and Anna have been inserted along with their respective details. Until now, we have saved a couple of employees in our database. Now, let's learn how to query the database in the Spring Boot and retrieve data. First, I will comment out the save operation we wrote earlier. This is important because if we start the application again, it will try to save the same data, causing a unique constraint violation exception. The first thing I will show you is how to get the total record count of a database table in Spring Data JPA. The Spring Data JPA provides a method called count, which returns the total number of record presents in a table. Let's check it out. We'll use system.out.println to print the total employee count. Number of employee count is, then concat with employee repository.count. Now let's run the project. In the console, you will see a query executed to count the records in the employee table. The total number of employees printed as well. Notice how easy it is to get the result just by using the count method without writing any custom queries. Next, let's retrieve the data of our first employee, John. We'll use the ID to fetch the record. If you remember, John was our first database entry, so his ID is 1. To find an employee by ID, we use find by ID method provided by the employee repository. This method requires the primary key as a parameter. Since our primary key is type of long, we need to pass 1L to represent the ID. The find by ID method returns an optional. If the data exists, we print the employee details. If present or else, inside this we will use an arrow function to handle the result. If the employee data is present, the function will print the employee in the console. If the data is not found, another arrow function will handle this case, printing no employee with ID 1 is found. Now, my IDE is suggesting a refactor. It says the lambda expression can be replaced with a method reference. Let's go ahead and replace it. The method reference makes the code a little cleaner and easier to read. Let's start the application and see the output. In the console, you'll see a query to fetch the employee record by ID. It also prints the employee data, but right now it's showing the object reference instead of readable information. Let's fix it. Opening the employee class. Here we need to add a toString method. This method will define how the employee details are displayed when printed. Generate toString, select all and OK. After generating the toString method, let's start the project again. Now closing the employee class tab, run the project. Now you can see the employee data displayed clearly in the console. The first name is John, along with the other details like last name, email, hire date and salary. That's how easy it is to query and retrieve data using Spring Data JPA. Now that we have accessed data from the database, it's time to explore the delete method. Let's try to delete John from the database. To delete an employee, we use the delete method provided by the employee repository. There are a couple of options. We can pass the entire entity to the delete method, or we can use delete by ID and simply provide the ID. I will use delete by ID and pass the ID of John, which is 1. After deleting the data, let's check the remaining employees in the database. To do this, we'll copy the line we used earlier to get the total employee count and print it again. Let's change the text. Number of employee count after deleting is. Next, let's try to access the employee with ID 1 after it has been deleted. We will reuse the earlier code to query the database and handle the result. Now, let's run the project. In the console, you'll notice several queries being executed. First, there's a query to count the number of employees in the database before deletion. The count is 3. Next, we query the database to fetch the employee with ID 1. After that, there is a delete statement that removes the employee from the database. And finally, we count the employee again, and this time the count is 2. Since John has been deleted, the total number of employees is now 2. When we query the database again with the employee ID 1, it shows that the employee is no longer available, displaying the message, no employee with ID 1 is found. Now, let's try something else. We'll access all the employee data from the database and print it out. To do this, we'll use employee repository.findAll. Then, we will iterate through all the data using for each loop. Here, we can use arrow function to handle each employee and print the result. My IDE is again suggesting a refactor. It says the lambda expression can be replaced with a method reference. So, let's go ahead and clean it up. It looks a bit nicer now. Alright, let's start the project again. Now in the console, you can see the query to fetch all employees from the database. It's printing each employee details right here in the console. Here is the data for Jane and Anna. Both entries are displayed as expected. Now let's open our employee repository again. Since we extended JPA repository, we automatically get access to several built-in methods like find all, save all, delete, and many others. These methods come included with JPA repository. But what if we want to customize this further? For example, what if we want to fetch the data by email? Remember, we have a field named email in our employee class. Let's take a quick look. Here it is our email field. Now, what if we want to retrieve a user by their email address or maybe by their first name or last name? How do we do that? If we check the available methods in employee repository, you will notice something interesting. In your ID, type employee repository, then dot, and it will show all the available methods. You will see that we can only query data using predefined methods like find by ID. But to fetch data based on custom requirements, we need to define our own query methods. Fortunately, Spring Data JPA makes this really simple. In the employee repository, we define the necessary methods for our custom queries. For example, let's create a method to fetch user by their email address. First, we define the method's return type. In this case, we will use optional employee as the return type because the result might or might not exist. Now, let's type the method name. If you start with find, the IDE will suggest method names for you. You can use find by or something more descriptive like find employee by. Let's go with find employee by. It's more descriptive. Next, the IDE will suggest fields from employee class. We want to fetch data by email, so we select email. Finally, we add the email parameter to the method, and that's it. Now, let's talk about why we are using optional in the find employee by email method. Since we know that the email field is unique, searching by email will always return at most one result. This makes optional the perfect choice for handling the result. Alright, let's head back to our Spring Data JPA application class. In the command line runner, let's use this method to find an employee by email. Let's say we want to find Jane using her email address. First, we'll copy the Jane's email address. Then, we'll add a log to indicate what we're doing. Something like find by email, followed by the email address. To fetch the result, we will use employee repository.find employee by email and pass the Jane's email address. Next, we'll check if the data is present. If exists, we'll print the result. Otherwise, we'll display a message saying no employee found with this email. Now, here's the magic. When we define this method, Spring automatically generates a query based on the method name. In this case, it will search the database for employee by email. Let's run the project. In the console, you can see the log added, find by email. Then there's a select query generated by Spring to fetch data where the email matches. And just like that, it finds Jane in the database. There's the beauty of Spring Data JPA. It makes queries so simple and elegant. Now, let's take this step further. This time, we'll fetch a list of employees based on their last name. If we check our database, we have two employees, Jane Doe and Anna Doe, both with the last name Doe. When we query the database by last name, we should get multiple results. So, for this case, we will use a list as return type. Let's go back to the repository and define a method to find employee by last name. Let's tweak this method to ignore the case sensitivity. This tells Spring to ignore the case when searching for the last name. Now in the command line runner, we'll use this new method to find employee with the last name Doe. We will iterate through the results using a for each loop and print each employee's details. To keep things organized, let's add a log before calling the method find employee by last name. Let's run the application again. In the console, you will see the log find employee by last name. Then the two matching employees, Jane Doe and Anna Doe, are printed. Great. Now let's add another employee with a different last name to test this further. We'll create a new employee named Kobir Hussain. First name Kobir, last name Hussain, email kobir@learnwithiftekhar.com. Salary the same as the others. We'll save Kobir to the database and run the project again. If we check the database, you will see the new employee Kobir Hussain has been added. Now, when we query by last name Doe, we should only get Jane and Anna but not Kobir. Let's check. Here in the console, we only have Jane and Anna. Finally, let's query by the last name Hussain instead. Before running this project, we'll disable the save operation for Kobir to avoid duplicates. Run the application and there it is. The console shows only one result, Kobir Hussain. Fantastic. That's how we can customize queries and use Spring Data JPA to fetch data efficiently. Now, let's try something more complex. This time, we will query the database using both the first name and last name of an employee, and we will make sure to ignore case sensitivity. First, we need to define a method in our employee repository. Optional, we will name it find employee by first name, ignore case, and last name, ignore case. And it will take two parameters, the employee's first name and last name. Since the combination of first name and last name is not guaranteed to be unique, this method will return a list, not an optional. Now let's use this method in our command line runner. We'll add a log, find employee by first name and last name. Then call the method from employee repository with the first name Anna and last name Doe. Next, we'll iterate through the list and print each employee's details. Let's run the project and see the result. This time, everything works perfectly. The console shows the log, find employee by first name and last name. Here is the query printed. Then, it prints the employee details for Anna Doe. That's how you can use Spring Data JPA to write more complex queries while keeping your code clean and efficient. Now, in our employee repository, we have defined custom methods for queries. But you might be wondering, how can you figure out how to define your own methods? What is the naming strategy? Well, let's check the official documentation for Spring Data JPA. First, search for Spring Data JPA on your browser. Here's the official site. Let's go ahead and open it. Go to Learn section. I will navigate to the reference documentation for this version. Inside the JPA documentation, on the left sidebar, you will see a menu item called Defining Query Methods. Click on that. Here, you will find all the details about how to define the query methods. There's plenty of useful information and I encourage you to go through it yourself for deeper understanding. Now, let me summarize what this section is saying. Here is the query creation section. It mentions that the query builder mechanism built into the Spring Data repository infrastructure is useful for building constructing queries over entities of the repository. What does this mean? This means that Spring Data provides a built-in system called the query builder mechanism to automatically generate database queries for you. You don't need to write SQL manually for common operations. Instead, you can use method names to describe what the query should do. Now, below that, we'll find another important part of the documentation. It says, parsing query method names is divided into subject and predicate. The first part, find, by, exist, by, defines the subject of the query. The second part forms the predicate. Let me simplify this for you. When you define a query method in Spring Data JPA, their names are broken into two parts. The first part is subject, that is, introducing clause like find by, exist by, or count by. Here, let's scroll up a little bit. Here they have provided some example. Here you can see this first part. This is find. This one, find by. There you can see another find by. This tells Spring Data JPA what type of operation you want to perform. This is find by tells Spring Data JPA that we want to retrieve data that matches a condition. Here are some other common examples including clauses. Exist by, check if data exists for a given condition. Count by, count how many records match a condition. Delete by, remove data that matches a condition. The subject can also include extra details to make the query more specific. For example, find top 3 by, retrieve the top 3 results. Find district by, retrieves unique results. No duplicates. Then we have predicate. The predicate comes after the by keyword and defines the condition for the query. This part specifies the properties of the entity to filter on. For example, find by email address retrieves data where the email property matches the given value. Find last name retrieves the data where the last name matches the specific value. The documentation also explains another key point. Any text between find or other including keywords and by is considered to be descriptive. This means that any text between the subject and the by keyword does not affect the query. It's there to make the method name more meaningful. For example, in our case, in our employee repository, we have this method, find employee by email. Here, this find by is the subject. This defines what operation we want to do. Also below in this method, this find and by, which is subject. Then we have predicate, that is the condition. For this first method, we want to query by email. This comes after this by, and here is email. For this second method, this is last name, and this is first name and last name. The text between those subject and predicate, this is employee, does not affect the query. It's there to make the method name more meaningful. Here with the predicate, we have added extra command ignore case. This tells Spring Data JPA to generate a query which will not case sensitive. This structure makes query method in Spring Data JPA both flexible and easy to understand. You can learn more about this from documentation page. And I highly recommend checking out the section on JPA query methods. Here, you will find a list of keywords you can use to define your query methods. For example, distinct to retrieve unique results and to combine multiple conditions, like to perform pattern matching. And there are many other useful keywords available. Feel free to explore this section on your own and experiment with the different options. It's a great way to build your understanding of Spring Data JPA query methods. We have seen how powerful Spring Data JPA is. It can handle complex queries effortlessly and fetch results from the database. But what if you want to use your own custom query? Spring Data JPA has a solution for that too. For example, let's take the find employee by email method. While Spring Data JPA can effectively generate a query for this, it also gives you the option to define your own custom query. If you do, Spring will execute your custom query instead of generated one. Let me show you how to do this. We can define a custom query using the query annotation. Inside the annotation, we will provide the custom query. For example, select E from employee, then the alias E, where E.email equals, then the question mark 1. This question mark 1 is a propositional parameter. It acts as a placeholder and will be replaced with the actual value when the query is executed. In this case, it will be replaced by the email address. Now, when we run this query, Spring will execute our custom query instead of generating one. In the console, you can see the custom query for finding by email, and it gives us the same result as before. Now, this was an example with one parameter, but what if we have multiple parameters? Let's take the find employee by first name and last name method. We'll add a custom query for it. Select E from employee alias E, where then we need to uppercase the first name and equals question 1, that is our first positional parameter, and uppercase the last name, then question mark 2, that is our second positional parameter. Here this 1, question mark 1 represents the first parameter, which is the first name, and question mark 2 represents the second parameter, which is the last name. The order of those positional parameters is determined by their numbers. So the first method parameter replaces question mark 1 and the second parameter replaces that question mark 2. This way, we can handle queries with multiple properties and customize them as needed. Now, there's a potential problem with defining queries using positional parameters. If you are only dealing with 1 or 2 parameters, it's manageable. But in more complex situations, where you might have multiple positional parameters, or when the same parameter is used multiple times in the query, it can become difficult to track. Fortunately, Spring Data JPA provides a solution for this, named parameter. Let's see this in action with the query method. Find employee by last name ignore case. We'll modify the query like this. We'll replace this question mark 1 with last name. This name parameter starts with colon followed by the parameter name, making them easier to read and manage. Next, we need to map this name parameter to the method parameter. To do that, we use the param annotation from Spring Data JPA. Our parameter name is last name. Let's run the project now and check the result. The project starts and in the console we can see the employee count, the result of querying by email, this return chain 2 as expected. But when we query it by last name, using the new query, we are not getting any results. Let's troubleshoot. Here is the issue. In the query, we are uppercasing the last name field, but we are not converting the method parameter to uppercase. Since we have ignored the case in this query, the database expects both to be uppercase. To fix this, we will modify the method parameter in the query. Use upper in the parenthesis colon our name parameter last name to convert the parameter value to uppercase before comparing it in the query. Let's apply the same fix to our other methods. For example, find employee by first name and last name will uppercase both positional parameters. Now let's run the project again. This time everything works as expected. The query by last name now correctly returns Kabir Hussain when we searched with Hussain, and the query using both the first name and last name returns the matching results from the database. Using named parameter not only makes queries more readable but also helps avoid issues in more complex situations. Spring also provides a way to write fully native queries. Let's try writing one now. First, let's check our database. Suppose we want to create a custom query here. The employee's last name is Doe, ignoring case, and their salary is greater than $2,000. To do this, we'll define a new method in our employee repository. Since the result may include multiple employees, the return type will be list. We'll name the method find employee by last name, ignore case, and salary greater than. This method will take two parameters, the last name as string and the salary as double. Next, we will annotate this method with query to provide our custom query. Select all columns from employee. Employee is the table name. We need to ensure the comparison is case insensitive. So we need upper last name, then the name parameter last name, and salary greater than named parameter salary. Those named parameter will be replaced with the actual method arguments. Since this is a native query, we also need to specify native query to true in this annotation. Now let's call this method from our command line runner and test it. We'll add a log, find employee by last name and salary greater than $2,000. Then we'll call the method and pass the last name as Doe and salary as $2,000. Let's run the project and check the results. There is an error. Let's troubleshoot. The issue is that we use the wrong column name. Last underscore name, matching the database column. Also, we need to annotate the method parameter with param last name for last name and param salary for the salary. Run the project again. Now the project starts, but I forgot to iterate through the results. Let's add a for each loop to print each employee's details. Run the project again. This time everything works. You can see the native query executed in the console. Select everything from employee where uppercase last name equals uppercase Doe and salary greater than $2,000. And here is the result, employees matching the criteria. That's how you can use native queries in Spring Data JPA to handle specific database operations. Now, let's run how to delete data from the database. For example, say we want to delete an employee by their email address. To do this, we'll create a new method in the employee repository. The method will return an integer to indicate how many rows were affected. According to Spring Data JPA's method declaration strategies, the method name is divided into two parts. The first part, delete employee by, indicates that what we are doing, deleting an employee. The second part, email, specifies the condition for deletion. The method will take email as a parameter. Although this method can work without the query annotation, I will add it explicitly to define the query. Delete from employee e where e.email equals. Here, email is a named parameter that represents the email address to match. Don't forget to add param annotation to the method parameter so that the Spring knows how to map it to the query. Now, let's use this method in our command line runner. First, we'll add a log, deleting employee by email. Before deleting the employee, let's count the number of employees in the database and log it. After deleting the employee, we'll count the employees again and log the new count. Let's run the project and see what happens. There is an error. The console shows an exception. Query executed via getResultList or getSingleResult must be a select query. Here's what happening. Spring is trying to execute the delete query using an approach meant for select queries. By default, Spring Data JPA assumes that methods annotated with query annotation are used for retrieving data. So, it tries to process the delete operation as if it were a select query using the methods like getSingleResultList or getSingleResult, which are specifically designed for queries that return data. However, since delete queries don't return any data, this causes an error. To fix this, we need to explicitly tell Spring that this is a modifying query, not a select query. We can do this by adding the modifying annotation to the method. The modifying annotation tells Spring to treat the query as an update or delete operation, allowing it to execute correctly. Let's fix it. In our repository interface, we will change the return type of the delete employee by email method to void, since we are deleting something from the database, and for now, we don't need to know the number of rows affected. Next, we'll add the modifying annotation to this method. Now, let's run the project again. There is another exception. Let's check the error. It says executing update or delete query and mentions a transaction required exception. The transaction required exception occurs because Spring requires a transaction to execute update or delete queries. In our case, delete employees by email method uses a delete query, and since it modifies the database, it must be executed within a transaction. However, we have not explicitly declared or enabled transaction to this operation. To fix this, we need to annotate this method with transactional. This ensures the delete operation runs within the transaction and completes successfully. Now, let's run the project again, and sure enough, the data is deleted from the database. Before deleting, the number of employees was 3, and after deleting by email address, it's now 2. Let's verify this from the database. Here you can see we have Anna and COVID. Jen Doe is no longer in the database. Fantastic! So far, we have explored many methods in the employee repository to access and modify data in the database. Now, let's divide into sorting the data. Since our repository extends from JPA repository, which further extends list, paging, and sorting repository, we already have access to methods for sorting and paging. Currently, our database only has 2 records. To demonstrate sorting, we need more data. Before we add new data to the database, let's do some cleanup. Let's open our Spring Data JPA application class. Here, the command line runner method, I am going to remove all the existing code to start fresh. But don't worry, I have already uploaded the source code to GitHub. You can check the repository using the link provided in the description. Let me show you. Here is my GitHub repository for this project. If you click on main, you will see the drop-down menu. Switch this section 1 branch. This branch contains all the code and implementation we have done so far in Spring Data JPA. Alright, now let's move forward. As I mentioned earlier, I will seed the database with some fake data to work with. For this, I will use a Java library called Faker. Here is the GitHub page for the Java Faker library, and you will find the URL in the description as well. Let me quickly show you how we can use this library to generate realistic fake data. First, we need to add the Faker library as a dependency in our project. Let's copy the Maven dependency and open the pom.xml file. Here are the dependencies we added previously. I will add the Faker dependency just before this section. We need to update the project dependencies. Right click on the project, go to Maven and select record project. Now our dependency is updated and we are ready to use Faker. Let's generate 100 employees using this library. First, initialize our Faker. Next, we will use a loop to generate 100 employees record. For each iteration, we will create a new employee and provide Faker generated data for the fields. First name, faker.name.firstname. Last name, faker.name.lastname. Now email, faker. Let's extract the first and last name into separate variables. For the email address, we will concatenate the first and last names in lowercase separated by an underscore and append learnwithiftkhar.com. That's it. First name, making it lowercase, concatenate it with underscore, again concatenate with last name to lowercase and concatenate it with learnwithiftkhar.com. Now for the hire date, we'll use faker to generate a random hire date. It is type of local date. The first parameter is we need to provide the year when we have hired the employee. Let's use our faker library to generate the year. So faker.number and choose the number between, let's say we have started to hire our employee in 2018 and the current year is 2024. Then provide the month. So again faker, the number of the month is between 1 and 12. Let's fix it into multiple lines. Now as a final parameter, provide the day of the month. That is faker.number and this one is number between, let's say it's between 1 and 28. So year between 2018 and 2024, a random month between 1 and 12 and random day between 1 and 28. This ensures the hire date is realistic. Finally, we will generate the salary using the faker's number generator. Set it to 2 decimal places, specify a minimum salary of $1,000 and a maximum of $5,000. Once all the fields are populated, we'll save the employee to the database using employee repository.save. Before running the application, let's clear all the existing data in the database. I'll open the database tool, open the query console. Here is the query console. I'm going to write truncate table query to remove all the data from employee table. Truncate table, it is public table and employee. Let's run the query. Execute the query. Our table is truncated. Let's refresh the database to verify. Yes, the table is now empty. Alright, let's run the project. You can see multiple insert statement in the console, which means 100 employees record have been added. Let's refresh the database and check the table. Here it is. All the data has been inserted successfully. We have employees' name, email address, salaries and hire dates, all generated dynamically using faker. Now, to keep the code clean, I'll refactor the employee generation logic into a separate method. Right click, select refactor and extract the method. Let's name it generate employee. Whenever we need to see the database in the future, we can simply call this method. For now, I'll remove the call to keep things tidy. The necessary data is already in the database. Now it's time to move to the sorting. Now let's dive into sorting the data. As we have mentioned earlier, since our repository extends from JPA repository, we already have access to all the necessary methods for sorting. For example, if you type employee repository dot find all, you will notice that there are two variations. One that retrieves all the data and another that accepts a sort parameter. There's also a method for pagination combined with sorting, which we will explore shortly. For now, let's focus on the find all method that accepts a sort parameter. Here's how we can sort the data. First, create a sort object using sort.by. Set the direction to ascending using sort.direction.asc and specify the field to sort by. Let's sort by the first name field. Remember, this field name must match the one in the employee class, not the SQL column name. Next, iterate over the sorted results and print each employee's first name to verify the sorting. Let's run the project. Here's the result. The employees are sorted in ascending order by their first name. The name starting with A appears first, followed by B, C, and so on. Now let's refactor this by including a variable for the sort logic. We'll name it sort. To sort the data in descending order, change the direction to sort.direction.desc. Run the project again, and you'll notice that name starting with Z appears first, while name starting with A at the bottom. We can also change sorting criteria. For instance, after sorting by first name, we can add a secondary sort by salary in descending order. Let's run this. In the result, you'll see that the names are still sorted in ascending order, but for employees with the same first name, their salaries are sorted in descending order. Now, let's refactor this logic into a separate method. I will extract it, name it sort data, and remove the method call for now to keep the code clean. So, we have successfully learned how to sort the data. But what happens when you have a massive data set, like a million records? It's not practical to load all the data into memory at once. Instead, we can retrieve the data in smaller chunks using pagination. Let me show you how to paginate the data. In our Spring Data JPA application class, let's use the findAll method with this pageable as a method parameter from the employee repository. The first step is to create a page request object. Pass the page number, starting from 0 for the first page. Let's say we are on the first page, so the value is 0. Specify the page size. Let's fetch 10 records per page. And finally, define the sorting criteria. For example, we want to sort by ID in ascending order. Now, pass this page request to the findAll method. The return type of this method is a page object, which contains the data for the current page and additional metadata like total pages and records. Let's iterate through the results and print the data. Running the project, you can see the first 10 records are loaded and printed in ascending order by ID. Pagination allows us to effectively handle large data sets by working with smaller chunks of data at a time. The project is now running, and you can see the query and the list of data in the console. We retrieved 10 employees from the database, but displaying the results in the console is a bit boring. Let's make it more interesting by displaying paginated employee results through a REST API. In our home controller, let's add a new endpoint. As I mentioned earlier, we are focusing on Spring Data JPA, so I will keep it simple and just demonstrate the pagination. Let's create a get mapping with the endpoint employee. The method will return a page object from Spring's data.domain package typed to employee. Inside this method, we will reuse our pagination logic. By copying the code, we have used the command line runner and injecting the employee repository into the controller using dependency injection. To do that, declare private final employee repository and generate a constructor for dependency injection. Now, instead of iterating through the employees, we will simply return the page object directly. Let's start the project and test this endpoint. We can use the Postman, but since this is a simple GET request, we can also test it using the browser. Open the Chrome and go to localhost 8080/employees. Here it is. The result is nicely formatted in JSON. The response shows the details like the total number of pages, the page size, and the current page number starting at 0. For example, with 100 employees and 10 per page, we will have 10 pages. And the first page, page 0, shows the first 10 employees including their ID and other details. Now, let's make it dynamic so we can fetch data for any page number through the URL. We will modify the method to accept a page number as a query parameter. Add a request param to fetch the page number from the URL. Set the default value to 0, the first page, and parse it into an integer. Let's run the project and test it again. The URL will look like this: localhost 8080 employees. Then we have the query parameter page and equals to. This will fetch the third page of data as pages are 0 indexed. Now let's try to check the next 10 data. Page is 3 and it shows the next 10 results starting from ID 36. This is how you can dynamically paginate data from the database using Spring Data JPA. Now let's move on to the relationships. Before that, I'll refactor the pagination logic into a separate method named paginated employees for better code organization. We'll call this method from the command line runner and push the updated code to GitHub. Now let's clean up and focus on relationships. Each employee has an address, forming a one-to-one relationship. Each employee can have only one address. Each address belongs to a single employee. This is a bi-directional relationship. Let's start by creating a new Java class named address and marking it as entity. Use the entity annotation and name it address. Add a table annotation and specify the table name as address. Next, define the primary key and other properties. For the primary key, let's copy the code from employee and paste it here and modify it to create a unique sequence named address_sequence. Now add the properties for the address. Street, type is string, add a column annotation with name street and nullable to false. For the city, type is string, add a column annotation with name equals city and nullable to false. For the state, type is string, add a column annotation with names, this is state and nullable is false. For the zip code, this will be type of string, add a column annotation with name zip_code and make nullable to false. Next, generate the constructor for this class. Include all fields except the ID as it will be generated automatically. Also, creating a noargs constructor. Now that the address class is nearly complete, let's generate the getter and setter method. Select all the fields, click OK, and we are done. Our address class is now complete. Next, we need to create the relationship between employees and address. To do this, let's add a new property in the address class. Before the constructor, add private employee. This establishes the link to the employee entity. However, you'll see an error because we have not defined the relationship yet. Let's fix this by making it as a one-to-one relationship and adding the join column annotation. In the join column annotation, set the name property to employee_ID. This represents the column name in the address table that will refer to the ID of the employee table. Set the reference column name property to ID. This indicates that the employee ID in the address table will hold the value of the ID column of the employee ID. If we check the entity relationship diagram, the address table has a column named employee ID, which refers to the ID column in the employees table. This completes the one-to-one relationship setup between employee and address. Now, there's one more thing we need to add in the one-to-one annotation in our address class, the Cascade Type. For now, we'll set the Cascade Type to all. Don't worry, I will explain what Cascade Types are in a moment. With that, our address class is complete. Next, we need to create a repository for our address entity. Let's create a new Java interface named address repository. Since we only need basic CRUD operations like saving data, we'll extend CRUD repository, not JPA repository. Specify the entity class address and the data type of the primary key, which is in this case is long. Now our address repository is ready. Let's run the project to check the query generated for the address table. Here in the console, you can see that a new table named address has been created. It includes an employee_ID column, which references the ID column in the employee table. A sequence for the address primary key is also created, along with the foreign key constraint linking the two tables. Let's verify this in the database. Refreshing the address, we see the new address and employee tables. Now, let's write an SQL query in the query console to check the data. We'll join the employee table with the address table using their IDs. The SQL query will look like this. Select everything from employees, E, join address A on E.id equals E.employee_ID. Running the query, you see no data at this moment since the tables are empty. Let's save some data into the database and check it again. Closing the query console, let's head back to the Spring Data JPA application class. Here in the command line runner, we'll inject the address repository alongside the employee repository. Let's split this into multiple lines for better readability. Now, let's save an address. We'll use the faker library to generate the address. Create a new address object. For the constructor parameter, we'll use the faker library to generate the address. Street faker.address.streetaddress. For the city, faker.address.city. For state, address.state. And finally, zip code, faker, address, and zip code. Additionally, we need to associate this address with an employee object. In the address class, we previously added an employee property. Let's generate a new constructor that includes the employee along with the other address properties. Now, for the employee, we will reuse the employee generation logic from our earlier generate employee method. Copy the relevant code and pass the generated employee to the address constructor. Finally, save the address to the database using address repository.save. Let's run the project again. In the console, you'll notice that Spring has executed insert queries for both the employee and the addresses. Here is the interesting part. We did not explicitly save the employee using employee repository. Instead, we passed the employee to the address and saved the address. Spring, thanks to the Cascade Type all, detected that the employee was unsaved and inserted it into the database automatically. Let's verify this in the query console. Reopen the previous query to join the address and employee tables. Running it, we now see the data. Let's transpose the result for a cleaner view. The employee ID is listed alongside the address details, including city, state, zip code, and other generated fields. This confirms that the one-to-one relationship between employee and address is working perfectly. Now, let's understand why saving the address entity also saved the employee entity. Earlier, when we created the address class, we defined its relationship with employee using the one-to-one annotation. If you recall, we also specified Cascade equals Cascade Type all. Let's move this annotation to a new line for clarity. The Cascade Type all setting is what allows the employee entity to be saved automatically when we save the address entity. So, what exactly is Cascade Type? Cascade is a mechanism in JPA that propagates the operations from a parent entity to its associated child entities. When we use Cascade Type all, it includes all Cascade operations. Let's take a look at the other Cascade options. Cascade Type persist. When you save the parent entity, in this case the address, any associated child entities like the employee are also saved to the database. Then we have Cascade Type merge. If you update a persistent parent entity, any changes made to its child entities are also updated or merged in the database. Then we have Cascade Type remove. When you delete the parent entity, any linked child entities are also deleted. For example, if you delete an address, any associated employee data will also be deleted. We also have Cascade Type refresh. This updates the state of a detached child entity with the latest data from the database. This Cascade Type is not commonly used. Then we have this Cascade Type detach. If you detach a parent entity from the persistence context, this Cascade Type also detaches its child entities. Then we have this Cascade Type all. This is a shorthand for combining all the individual Cascade operations: persist, merge, remove, refresh, and detach. While it's convenient, you should use it cautiously, as it might lead to unintended side effects or performance issues for more complex applications. For now, we are using Cascade Type all because it is a simple application and it works well for our use case. That's how cascading ensures that when we save the address, the associated employees is also saved automatically. Now, let's close the address class and move on to something important. Let's try to fetching address data from the database. We'll use address repository.findAll to retrieve all the addresses and iterate through them to print the data. Let's run the project. The data is not showing properly. That's because we have not provided a toString method in the address class. Let's generate it now. Okay, Running the project again. Now you can see the data. Here is the issue. Since we have saved data multiple times earlier, the database has 3 entries. Let's comment out the saving logic for now, as we don't need to add new data at this point. Now, here's something interesting. Even though we are fetching only addresses, you can see that the console shows a select query for employees as well. Why is Spring fetching the employees when we are only asked for address? The answer lies in the one-to-one annotation. If we look at the annotation, there's an attribute called fetch, which defines how related data is loaded. For one-to-one relationship, the default fetch type is eager. What does this fetch type mean? Fetch type eager, when we load the parent entity, in this case address, Spring also loads the associated child entity, that is employee, immediately. Then we have fetch type lazy. With these, the child entity employee is loaded only when explicitly requested, not when the parent entity, that is address, is fetched. For one-to-one relationship, the default fetch type is eager because there's only one associated child entity. For one-to-many or many-to-many relationships, the default fetch type is lazy, as there could be many child entities and loading them all at once could be inefficient. Now, let's talk about unidirectional and bidirectional relationship. In our address class, we have added a relationship to the employee entity. This allows us to access the employee object from the address object. However, if we check the employee class, there's no reference to the address. This means we can access the employee from the address, but we cannot access the address from the employee. Then we have the bidirectional relationship. To make this relationship bidirectional, we need to add a reference to the address in the employee class. Let's add a new property, private. This is our address. Mark it as a one-to-one relationship and specify the mapped by attribute. The mapped by value should match the name of the property in the address class that defines the relationship with the employee. In this case, it's employee. Now, generate getters and setters for this new property. This forms a bidirectional relationship. Now, when you load an employee, the associated address will also be fetched. Let's test this. First, fetch an address by its ID using address repository find by ID. Check the database for an ID to use. Let's use this address. The ID of this address is 2. So, here in this field, my ID method provides 2. If present, we will print the data. Let's run the project. The address is fetched successfully. Next, let's fetch the associated employee by its ID. In our case, the employee ID linked with this address is 107 using employee repository dot find by ID, provide the employee ID. Print the employee's detail. Run the project again. In the console, you notice 2 important things. The employee query includes left join with the address table to fetch the associated address. And the address query also includes a left join with the employee table to fetch the associated employee. This shows that with a bidirectional relationship, we can fetch the address from an employee table and vice versa. Now, let's talk about deleting entities in a relationship. In our case, an employee has a one-to-one relationship with an address. If we delete the employee, it makes sense to delete the associated address as well. However, if we delete the address, it does not make sense to delete the employee, as we might just be updating the address with a new one. To handle this, we use the Orphan Removal attribute to the one-to-one annotation. By default, Orphan Removal is set to false, meaning the child entity, like the address, won't be automatically deleted when the parent entity, like the employee, is removed. Let's try deleting the employee and see what happens. Back to the Spring Data JPA application, we will delete an employee and check if the associated address is also removed. Let's test it. Let's try deleting an employee using delete by ID method from the employee repository. We will delete the employee with ID 206. Running the project, you'll notice 2 queries in the console. A select query for the employee, another select query for the address associated with the employee. However, there's no delete query. Why is that? Hibernate prevents us from deleting the employee because it's linked to an address. To allow the deletion of both the employee and its associated address, we need to enable orphan removal in the one-to-one annotation. Before making this change, let's verify the data in the database. Open the query console and run the following query. Select everything from employee, left joint with address on employee ID equals address.employee ID, where employee ID equals 206. Transpose the result. You will see that both employee and the associated address are still present in the database. Now let's update one-to-one annotation in the employee class by setting orphan removal to true. Run the project again. This time the console shows a delete query. The employee is deleted and the associated address is also deleted. Let's run the database query again. Now you will see the result is empty. Both the employee and the associated address have been successfully deleted. Now, a note on orphan removal. If you enable orphan removal in address class instead, deleting the address will also delete the employee. This does not make sense in most cases, as you might just be updating the address for an employee. Orphan removal is a powerful tool, but must be used thoughtfully to avoid unintended consequences. Now, let's see how to customize the name of the foreign key constraint. If you remember, in the address class, we defined a relationship with employee using the join column annotation. Here, we specified that the employee ID column in the address table refers to the ID column in the employee table. When we ran this project earlier, Hibernate automatically created a foreign key constraint. Let's check this in the database. Now, let's take a look at the foreign key constraint in our address table. If you notice, the foreign key is named FK, followed by a random string. This is automatically generated by Hibernate. But instead of this random name, I would like to give it a meaningful and custom name. This is simple to do. Let's modify the join column annotation in the address class. The join column annotation has a property called foreign key. Using these, we can define our own foreign key constraint. Here's how. Inside join column annotation, add foreign key equals, then annotation foreign key. Inside the foreign key, pass the desired name of the constraint. I will name it employee underscore ID underscore FK. One important thing to remember, the foreign key name must be unique. Since we already have a column named employee ID, adding underscore FK ensures that the constraint name is unique. Let's run the project and check the result. The project is running, but it does not update the constraint. Let's drop the existing foreign key constraint from the database manually. Now stop the project and run it again. In the console, you can see that Hibernate has created the foreign key constraint with the name employee underscore ID underscore FK. Let's verify this in the database. Refreshing the address table, under foreign keys, you can see we have this new constraint employee underscore ID underscore FK. It's always a good practice to define meaningful and consistent names for your foreign key constraints instead of relying on the default ones generated by Hibernate. So far, we have covered one-to-one relationship and learned quite a bit. From here, things will become more straightforward as you build on these concepts. In this section, we'll work on one-to-many relationships. Just like one-to-one relationships, we'll use specific annotations, one-to-many and many-to-one, depending on the perspective of the relationships. If you refer to the ER diagram, we can see that the relationship between employee and task is one-to-many. One employee can have multiple tasks. If we implement a bi-directional relationship, this also means many tasks can be assigned to one employee. Let's start coding. First, create a new class named task, collapsing the sidebar to focus on the code. Mark the class as an entity by adding the entity annotation. Provide a name for the entity, which is task. Specify the table name as task using table annotation. Next, define the primary key. Copy the primary key code from the employee class. paste it on task, modify the sequence name to task sequence for uniqueness. Now let's add fields to the task class. The first field is the task name. Add a private string name. Annotate it with column name equals name. Next, define the relationship with the employee entity. Add a field of type employee and name it employee. Mark this field with the many to one annotation, as many tasks can belongs to one employee. Use the join column annotation to configure the foreign key. Specify the name as employee ID, which will hold the employee ID in the task table. Set referenced column to ID, linking it to the ID column in the employee table. Add a foreign key constraint with foreign key name equals employee underscore task underscore fk for clarity. Make it nullable by adding nullable to false. Now let's generate the constructors and other boilerplate code. Generate a constructor for all fields except the ID, as it will be automatically generated. Create another constructor that only accepts a task name. Add a no argument constructor for frameworks like JPA. Generate getters and setters for all fields. Finally, generate a toString method to help with debugging. At this point, our task entity is complete. It includes a primary key, fields for the task name, and the relationship with the employee entity, annotations for table structure, foreign key constraints, and other relationships. In the next step, we'll explore creating a repository for the task entity and demonstrate how to manage data in the relationship. Alright, we have set up the relationships between employee and task. Let's run the project and see what happens. In the console, you can see the query. A new table named task has been created. It contains column for ID, name, and employee ID. Additionally, a foreign key constraint named employee task fk has been added. Let's verify this in the database. Refreshing the database, we now have three tables: address, employee, and task. In the task table, you can see the columns for the ID, name, and employee ID. If you check the foreign keys, you will notice the constraint employee task fk linking the task table to the employee table. To make this relationship bidirectional, we will now define a relationship between employee and task in the employee class. Opening the employee class, we will add a field of type set task to represent a list of tasks. Since one employee can have multiple tasks, we are using a set. Annotate it with one to many and set the map by attribute to employee to link it with the corresponding field in the task class. To ensure that when an employee is deleted, all the associated tasks are removed, we will set Orphan Removal to true. Instead of using Cascade Type all, let's be precise. We'll add Cascade Type persist to ensure tasks are saved when the employee is saved, and Cascade Type remove to remove task when the employee is deleted. Additionally, we'll add helper method for managing tasks. One method will allow us to add task to an employee and ensure the task employee field is also set. Another method will let us remove task from an employee and reset the employee field in the task to null. Now that we have completed the setup, let's test this relationship in Spring Data JPA application class. Let's do some cleanup, removing some of the previous code. Here, we have initiated the employee. After initializing the employee, we'll associate 3 tasks with them. Record a video, do some coding, and drink coffee. Finally, we'll save the employee using employee repository.save method. Running the project, everything works perfectly. In the console, you will notice queries for inserting the employee and the task. Interestingly, although we are saving only the employee, the tasks are also being saved automatically. This is thanks to the Cascade settings. By specifying Cascade Type to persist, Spring ensures that all associated tasks are saved along with the employee. To confirm the data, we'll query the database. Running a join query between the employees and task tables, select everything from employee alias E, left join task T on t.employee underscore id equals e.id. Execute the query. We can see all 3 tasks record a video, do some coding, and drink coffee associated with the employee. The result shows the task clearly linked to the employee, and the relationship is working as expected. With this, we have successfully implemented and tested a bidirectional one-to-many and many-to-one relationship between employee and task. This is a solid foundation for handling complex relational data in Spring Data JPA. Let's move forward. Now, it's time to discuss many-to-many relationships. Let's consider the relationship between employee and project. One employee can work on multiple projects, and at the same time, many projects can involve the same employee. To represent this, we'll use bridge table. This table contains the employee ID, which is the foreign key referencing the employee table. The project ID, which is a foreign key referencing the project table. The bridge table allows us to define many-to-many relationship between employees and project. Let's start by creating the project class. First, create a new Java class and name it project. Collapse the sidebar for better focus and add the entity annotation with the name set to project. Specify the table name as project. Next, we'll define the primary key. To save time, let's copy the primary key code from another class, maybe from address, and paste it here. Rename the sequence to project_sequence. Now, add a field for the name of the project, private string name. Annotate it with column name equals name and nullable to false to make sure the column is non-nullable. In a real-world project, you might have additional fields like description, start date, end date, and more. But for simplicity, we'll stick to just ID and name. Generate the necessary constructors. One constructor that includes the name field. Another new argument constructor for JPA. Next, generate getter and setters for all fields. Finally, generate a toString method for easier debugging. With that, our project class is complete. Now, let's move on the employee class to define the many-to-many relationship. In the employee class, add a field to represent the project associated with an employee. Private, set, type of project, project equals new. I'm using hash set. Using a set helps us avoid duplicates, but you can also use a list if that's more suitable for your use case. Annotate this field with many-to-many. Set the cascade type to cascade type persist and cascade type remove, just like we did for the task earlier. This ensures that projects are saved or removed when employees are saved or deleted. Now, add the join table annotation to define the bridge table. Name the intermediate table employee_project. Use join column to define the foreign key for the employee side. Set the column name to employee_ID. Add a foreign key constraint named employee project employee ID_fk. Next, define the inverse join column for the project side. Use join column again. Set the column name to project ID. Add a foreign key constraint name project employee project ID_fk. I know this name is weird, but just stick with that. The many-to-many relationship is now fully configured in the employee class. We define the bridge table, the foreign key constraints, and the relationships from both sides. This setup allows us to associate employees with multiple projects and projects with multiple employees seamlessly. Let's move forward and test this relationship. Now, it's time to configure the project entity for the many-to-many relationship with employee. First, we'll define a field to represent the employee associated with a project and annotate it with many-to-many. To ensure this relationship is properly linked, we'll set the map by property to match the corresponding field in the employee class. Generate getter and setter. Select employee, OK. Next, we'll head back to the employee class to define some helper methods. These methods will allow us to assign and remove projects for an employee. When assigning a project, we'll make sure to add the project to the employees list and Also, update the employee reference in the project. Similarly, we'll update both sides of the relationship to keep things consistent. Let's run the project. Everything works perfectly now. The console shows that a new table named Employee Project has been created. It contains the two columns we defined, Employee ID and Project ID, along with the necessary foreign key constraints. Now, let's assign some project to an employee and test it. We'll create two projects, Employee Management System and Payroll Management System, and assign them to an employee using the helper method. Run the project. The console confirms the changes with several queries, inserting the employee, adding the project, and linking the employee to the project in the employee project table. Let's check the database. Joining the employee project, and project tables, we can see that the employee is successfully associated with the two projects. Everything is working perfectly, and the many-to-many relationship is fully functional. Wow, we have come a long way in this tutorial. Let's quickly recap what we have learned. We started with the basics of Spring Data JPA, understanding relationships like one-to-one, one-to-many, and many-to-many. We saw how to define entities, configure relationships, use cascading operations, and manage database queries effectively. We also explored helper methods to simplify data manipulation and even tackled advanced use cases like custom queries and bi-directional relationships. What we have covered here represents the foundation, about 90% of what you will use in most projects. Those are the core concepts you will rely on time and time again to build robust applications. Of course, there's always something more to learn. Spring Data JPA offers a range of advanced features that are not used as frequently but can be incredibly powerful when needed. I will dive into those in future videos. So make sure to keep an eye on the channel. This is not the end. It's just the beginning of your Spring Data JPA journey. If you are ready to take the next step, check out the other videos linked on the end screen. Whether it's advanced JPA topics, Spring Boot, or other Java concepts, there's a lot more to explore. Thank you for watching. If you found this helpful, don't forget to like the video, leave a comment, and share it with others who might find it useful. Until next time, keep learning, keep building, and I'll see you in the next one. Bye bye.